Greetings. In this one, we're talking about the idea of cosets. And cosets are basically a certain situation when, let's say, we have some subgroup H, which is the subgroup of G. All right. So first, this is in general. Coset arises when one has a subgroup. Let me denote that H, very common letter to denote a particular group. G, it is the subgroup of. And so, right, H as a subgroup of G denoted in this lesser or equal sign. That's the way subgroups are denoted. That means that A is a subgroup of G. And a coset is basically a specific type of set defined in the following way, that for any element X inside the G group, the subgroup of which is H, I can have a coset defined in the following way, being a particular set as follows. I will define it as XH, where X is that one element from G and H is the set of the elements of the subgroup H, or the subgroup H in general. And it will basically be this set defined in the following way. X in operation with H, or XH without the operation sign. It's a quicker way to write it. In that way that all these lowercase h's are inside the uppercase h. Now, what this means is basically that when one creates a coset, it is a set which is created in the following manner. One takes one element from the group G and then takes its subgroup H, and the coset of that element X from G, denoted as XH, will be all the elements created in the way that I take that one element chosen from G and put it into G's operation with every element of H. So here there's nothing denoted, here there's also nothing denoted, but the point stays that here, although it looks like multiplication, what is actually meant here is the whatever operation. It can be addition even, or and so on. It can be other operations as well. Although this might seem like multiplication, doesn't have to be. In many cases, it is actually not at all multiplication. And I will give an example of this. And actually, I will give an example where it is not multiplication. It will be namely addition. So just once again to repeat this, one has a set, one has a group G and a subgroup H of that group G. Now one takes one element, arbitrary element X from G, and combines it in binary operation with each element of the subgroup H. And now each of these results gives a new element, and this new set consisting of all these new elements is the coset of coset called XH. Now this is called the left coset because X is on the left side and H is on the right side in the operation. This is the order. Then there's also something called right coset, which is completely similar, just the H goes first and then the X is second. And then the definition is also switched in the following way. And what this lowercase h means basically is the following. H is the entire group H and all its elements. And H is each element, all right? So one individual element. So it will be done that every element inside H, that's the lowercase h what it denotes, every single element of H will be combined with that particular X that had been chosen from G and in that binary operation. Alright, so this is the right coset when X is on the right. In the writing here, this is a left coset. They can have different results based on the operation case, based on the groups, but they also often don't have a different result. So very often left and right cosets are equal, but they don't have to be. Alright, so let's get to an example. So a good example could be, let's say, integers modulo 6. So integers modulo 6, what is meant by this is basically 0 to 5, all these individual integers, but with the counting idea of when one gets to 5 and adds another 1, one doesn't get to 6 because there's no more, but one goes back to 0. So there's this loop counting. That means 4 plus 2 is going to the right, but then returning to the first place. So 0. 0 plus 3 is normally 3. 3 plus 1 is 4, 4 plus 1 is 5, but then one goes more than that. 5 plus 3 is 1, 2 is 2. 2 plus 3 is 5, but 5 plus 2 is go back to the beginning and go 2 elements further, which will be 1. So 5 plus 1 is 0, 5 plus 2 is 1. That's examples of that. Now, this is called integer modulo 6, and a good subgroup example of this could be, for example, the group. Okay, so let's say that for this case, I will say that I have two groups, A and B, or maybe in general I could not, I don't even have to call them. I can just take this general, just say integer modulo 6, and the second group that I will use, that will be the subgroup of this. So the subgroup of it will be, because cosets are constructed in the way that one has a group and its subgroup. So the coset, so the subgroup of this group example could be 0 to 4. Why is that so? Well, it has, in the counting of basically going up until 6 and going back, it does have its identity as well as inverse, because when one goes from 0 to 2, there's possibility to go back to 0 using the 4. So there's an element that if added, because I will again say this, let's say this group will be Z6 with addition. So the first group is Z6 with addition, with this loop addition, right? Then this one will be also with addition, let's say, all right? So for this other group, which is a subgroup of this one, I also define addition. And in such case, I go back, refer back to these rules. Well, 0 plus 2, all right, I have this operation of addition, 0 plus 2, I add two elements. Is there inverse to that to get back to 0? Well, there is, I can add the 4. So I suddenly have, I don't have to use any minus 4 because there's none. But it is possible for me to get back to 0 because 2 plus 4 will get me back to 0. Alright? Or if I get from 0 to 4, I can add 2 and get back to the 0. So that will fulfill the inverse. And as far as identity, I have 0. That won't ever change it. So that's identity. Alright, so seeing that this is fulfilled and indeed this group is a subgroup of this integer modulo 6, I can start list out the cosets and we can spot one pattern. We won't go that deep into theory on this, just quickly show idea through this example, but there will be a spottable pattern which is quite nice. So the idea was that coset is basically x age with all the ages in the subgroup age, alright? So I take one element from the group, from the integer modulo 6 in this case. Let's say I will choose 1, and what I do with it is I combine it with each element of age. So this is each element of age. So what I will do is basically I will choose, let's say for the first one, I will choose 0. Alright, so I was going to start with 1, but I will actually do 0 first. So if I choose 0, what it does is basically I will have to create a new set. And I will call it, it's built basically in general, it is x, in general it is x age. Now with addition, because we're adding, the order does not matter. X age will actually in this case with this operation not be x age, it will be namely x plus age. But it could be also written as a right coset. That means h plus x. Doesn't matter in which order I say. So x plus h or h plus x. In this case does not matter. So going towards this, the point here is that the subset or this subgroup and this group will now be used to create that coset example. So basically, how many different cosets I'll get? Well, I will get as many. We'll just list and see which ones are identical, which ones aren't, because there will be some that will actually end up being identical. So the idea is pick one element from the group G in general, from the group which is not the subgroup, and then combine with each of the three elements or each of the elements of the subgroup. So I know there's addition, that's the define operation, and also it's under modulo 6. So what I have to do here is basically I'm taking 0 plus 0, 2 plus 0, and 4 plus 0. So this will be 0, 2, 4. The first one will stay same because 0 plus all of these terms will be still the same terms. Alright, so that's the first coset. The second coset is I'm taking the other element of z modulo 6, integers modulo 6. So it will be 1 plus each of these elements. Still won't go back in that manner of modulo 6 because it won't get all the way to the 6 and beyond. So it will be 1, then it will be 3, and then it will be 5. Alright. In the third case, I'm adding 2 to each of these because I'm taking this third element of the integers modulo 6. So I'm adding 2 to all of these. I get 2, then I get 4, and then I get 6, but it's modulo 6 That means it gets me all the way back to 0 again. Alright, so now I've got these 3. And the next 3, well, now I use 3. So I get 3, 5, and 7, well, it gets me all the way to 1. And what I start spotting is that this set is the same like this set. It's just different order of elements, but it doesn't matter in which order they are listed. So these are actually the same. Then I use 4, so I get 4, 6, well, 6 is already 0, and then 4, 8, that's actually 2. So 4 or 2, do we have it? 2, 4, oh, here. So it's the same one. And then the last one will be again 3 elements, and I pick the last element of the group, integers model 6, 5 namely, and I add it to all of these 3, which gives 5, 7 will be 1, and 4 plus 5 is 9, which will be 6, 7, 8, 9, 3. Like 1, 3. Alright. So now what we see here is a very nice pattern, a very interesting pattern. First of all, we can eliminate those that are repeated. So 0, 2, 4 and 4, 2 are the same. So I can say I can just, let's say, disregard one of them because I see they're same. Or instead of maybe crossing, I will just connect them to show that indeed we call them twice for various elements of G. If I call this the G and if I call this the H in this general coset structure, then for each element of G we repeated the operation of creating the coset with each of the elements of H in each case, and we see that actually there's 3 distinct sets now, and they are and then 3 that are repeated instances of the first 3. So basically this one is the same as this one. 1, 3, 5 is the same like 3, 5, 1, and then 4, 2, 0, 2, 0, 0, 2, 0, 1, 3, 5, 1, 3, 5, and then 5, 1, 3, 2, 4, 0, this one, this one. Actually, this one is repeated, this one is repeated, and this one is. So we only have 2 different ones. We actually have only 2 different ones. That's how it ends up in the end. And another thing is very interesting. The point here is that if we look at the only distinct sets we now have, we have 3, 5, 1, 5, 1, 3, that's 3, 5, 1. If I choose one of the versions of writing the order, I could also write the order in the order of the numbers getting bigger, so 1, 3, 5, it's maybe the best way, and in the second case 2, 0, 4. What's really nice to spot is we have no other sets with different elements than those. They all have the same number of elements, and they never have, let's say, the same element and then in combination with a different element. Either they have all the elements same, or they have completely the same, or each of the elements is different. So it's not like one element is same like in another coset and one is different. One element is different than in another coset and one is same. It is always the way that either all are the same, making it the identical set as a coset, or all are different, making it a distinct coset. So that's an interesting phenomena to spot here. And another interesting phenomena is in the context of partitions of the group. What is interesting is that the G, if I look at this as the G, as the group, the subgroup of which the 0, 2, 4 was, it got exactly partitioned into equal cosets or equally big cosets with the equal amount of elements. And none of them got repeated in either of them because I took just the distinct cosets. And I see that 1, 3, 5 and 2, 0, 4, well, they share no elements, but together, if I add these 2 sets, I get exactly the set of elements that the Z modulo 6 has. So that's the point here, that cosets indeed actually divide it, and they divide this group G into these 2 parts. And let's say in this example, what we found out, basically listed all the cosets according to the rules that had been presented, and afterwards basically ruled out those that were repeated, only looked at those distinct cosets because they were all either completely same or completely distinct. So just took the distinct ones and see that if we add them, we get basically a partition together. They partition this original set in the way that they include all the elements of this set, but they don't repeat any of those elements. This one has 0 to 4, but none of 0 to 4 appears in this one. In this one, the other 3 elements appear.